Good morning and welcome to this lecture on vibrations of plates and shells. So last time we took the example of a circular plate to look at the first fundamental form. We'll take a further example of a cylinder, a cylindrical surface. So let me draw here. Let's say this is a cylinder. And I will take my x axis along the central axis, then I have my y this way, and then my z this way. Okay, so this is y, this is x, this is z. So y, z are in this plane of the circle. Then I want to look at some point here. I want to look at a point here which is somewhere here on the shell. This is the point I want to describe. And I'm going to measure theta from here. Theta from here. Okay, theta is measured from z axis towards y. Okay, so let's see how we describe this particular point, that particular point. That is now parameterized in terms of x and theta. Those are my alpha 1, alpha 2. So that is equal to xi hat plus a sin theta j plus a cos theta k. This is E1, this is E2, this is E3. So del R del X is equal to I. That implies del R dot del R X, del R del X dot, okay, let me write del R del X dot del R del X is equal to 1 is equal to A1 square, implies A1 is equal to 1. Next, del R del theta, so I need to remind myself the form of R, a sin theta j plus a cos theta k. So del R del theta is given by a cos theta j minus a sin theta k. Okay, that implies del R del theta dotted with del R del theta is equal to a square cos square theta plus a square sin square theta is equal to a square, which is equal to a2 square, which implies that a2 is equal to a. So my length element is dx square plus a square d theta square. Okay, so here is a 1 which is a1 square, and this is a2 square. So what are these a1s and a2s doing? Okay, so what is the role of a1 and a2? The role of a1 and a2 are to convert a coordinate change into a length change, into a change in length. Change in length. Okay, so if we are looking at the rectangular plane case, okay, so we had dr, let's say, or ds like this way, then that leads to dx and dy. Okay, so that ds square is equal to dx square plus dy square. So there is a 1 here and a 1 here, which is a1 square, this is a2 square. So dx and dy are already in the length form, and therefore a1 a2 are 1 each, whereas in the circular plate, we have an r, let's say, then we have dr. Okay, so this is d theta and this is dr. Dr, that's radial length. Okay, so now if we look at this arc length, this is my ds, then ds square is equal to dr square plus this is r, and this is r d theta, so r square d theta square. So there is a 1 here, so that is a1 square, because dr is already in length, in the length coordinate, whereas d theta is angular, and therefore you need r square to convert it to a length. Okay, similarly the cylinder, if I take a cylinder, it's not good. If I take a cylinder, and then we have a differential element this way, differential length that way, and this is my ds, suppose ds, then ds square is equal to this length, which is a d theta, and it is dx, so it is dx square plus a square d theta square. There is a 1 here which becomes a1 squared, and this is my a2 squared. So here also a1 a2 convert a coordinate change into length. Okay, so the next idea is related to the unit normal to a surface and what is called the second fundamental form. Second fundamental form. So again, let's have a rectangular basis. This is X, this is Y, this is Z, and let's say I have alpha 1 and alpha 2 and alpha 3, and at some point I have the descriptor vector R alpha 1 alpha 2. So I want to describe the normal, local normal, small n unit normal, local unit normal. So that local unit normal n of alpha 1 comma alpha 2 is del R del alpha 1, which is tangential here, sits on the surface, crossed with del R del alpha 2, which is tangential to the surface in the alpha 2 direction, cross product of that divided by the magnitude of the same thing. So now this magnitude here, as we know, the magnitude of the cross product is magnitude of each of these sin theta. Okay, the angle between the two. So which is what? Which is equal to A1 A2 sin theta. Okay, theta is 90 degrees. Okay, so this is what in terms of our original fundamental form E, F and G, this is square root of E, G. Okay, sin theta. Let's keep it. Okay. Then the next one is the dot product. Okay, del R by del alpha 1 dotted with del R by del alpha 2, which is again equal to the magnitude del alpha 1 del R by del alpha 2 cos theta. Okay, which is again A1 A2 cos theta, or in the original first fundamental form root E G cos theta. Okay, so now what happens? This is F. Okay, this is F. So I have cos theta is equal to F over square root EG. And sine theta, which is square root of 1 minus cos square theta, is equal to square root 1 minus f square by EG, okay, which is equal to root of EG minus f square by EG. Next, if I bring this root EG here, I have root EG sine theta, okay, is equal to square root of EG minus square, and we will call this a new number h. Okay, so that what is it now? I have n, the unit vector given by del r del alpha 1 del r by del alpha 2 divided by h. Okay, and we say n points from the concave towards convex side. Okay. Now, the second fundamental form. The second fundamental form. So let me take a specialized example to illustrate. So I have a conical surface. I have a conical surface. How does it look? I have a circle, then the radius decreases, and at some point I will take again a plane, okay. So this is a circular curve, it's a curve, closed curve, circular, and the tangent here, tangent is like this at that point, it's in the plane of this circle, okay, and the principal normal of the circle is like this, because it has to lie in the oscillating plane. So this is the oscillating plane, the plane of the circle, okay. So this is the tangent, unit tangent. So this is the principal normal to the to this tangent, okay, to the curve at that point. However, if you see this conical surface, its normal is like this, its unit normal is in this direction, okay. So if a curve lies on a surface, its own principal normal need not coincide with the surface normal. So this angle we'll call it 90. So this is the tangent, okay, this is the tangent. So now what we are going to do is T dash, okay, this T dash being dt by ds, as we said, is what is the curvature times the principal normal on the curve. Okay, so that is equal to now we find its components in terms of the surface properties, which is curvature in the normal direction plus curvature in the tangential direction. Okay, this is the tangent to the, this is also a tangent, but that's tangent to the surface. Okay, I have a local normal here and a tangent here. Maybe I'll put a double bar to separate it from this tangent. Okay, so this is the, let's say, the K curvature vector. So Kn is the normal curvature vector and Kt is the tangential curvature vector. Okay, now Kn is equal to minus Kn, okay, or let me do this, let me give it a stylized scalar curvature value and the normal. They are opposite in sense, opposite in sense. Okay, now so Kn is in this direction, Kn is in this direction, in that general direction. Okay, or sorry, to give you the correct picture, it's in the opposite direction, it's in this direction, whereas n is in that direction. Okay, and n is still perpendicular to T bar. Okay, this is still perpendicular to this T bar. Why? Because it is normal to this. This curve has infinite normals. This circular plane has infinite normals. Okay, every direction there can be a normal. So K, this n bar happens to be one of the normals. So n bar is still perpendicular to T bar. And so n dot T is equal to 0. And if we take a derivative with respect to the arc length, okay, so this is the arc length, this is the arc length, then we have equal to 0, okay, which means what now? T bar dot dn by ds, plus n bar dot dt by ds equal to 0, okay, or dn ds dot t bar is equal to minus n bar dot dt by ds, okay, from kn is equal to minus k n bar, okay, minus k n dot n is equal to this kappa and n dotted with k, n bar dotted with k, which k? This k, okay, this k, which is equal to kn plus kt dot n, okay, which now implies that n dotted with dt by ds, okay, is equal to n dot kn, because this dot is 0, okay, which means my minus kappa is equal to minus dn by ds dot t, okay. So therefore my kappa is equal to dn by ds dotted with dr by ds. dr by ds is t, okay, this sign goes, dr ds is t, the tangent, please remember. So I can write this now as dn dotted with dr divided by dr dotted with dr, okay, this is ds square, so that is dr dotted with dr, okay. So now what? Now my dn is del n by del alpha 1 d alpha 1 plus del n by del alpha 2 d alpha 2 and dr is equal to del r by del alpha 1 d alpha 1 plus del r by del alpha 2 d alpha 2, which means my kappa is equal to what 2 by 1, which is equal to L d alpha 1 squared plus twice m d alpha 1 d alpha 2 n d alpha 2 squared by e d alpha 1 squared plus twice f d alpha 1 d alpha 2 plus g d alpha 2 squared. Okay, where now L is equal to del R by del alpha 1 dotted with del n by del alpha 1, then twice m is del r by del alpha 1 dotted with del n by del alpha 2 plus del r by del alpha 2 dotted with del n by del alpha 1, and n is equal to del r by del alpha 2 dotted with del n by del alpha 2. Okay. So, this is the second fundamental form. This numerator is the second fundamental form. Second fundamental form, and these are the LMN definitions, and they relate to the first fundamental form and produce the curvature. Okay. Now, it is important to note here that there are an infinity of curvatures on a surface based on which curve you take. So, if I have a curved surface, and I take a curve like this, or I take a curve like this, take a curve like this, I take a curve like this, every one of these curves will produce a radius of curvature and curvature. So, there are an infinity. Okay. So, let us say this is my alpha 1 and that is my alpha 2. Based on the direction, okay, based on the direction d alpha 2 by d alpha 1, I will get one kappa value. Okay. So, what should we do? So, what now we do is this: we substitute lambda for d alpha 2 by d alpha 1, okay, and then I get kappa written as L plus twice m lambda plus n lambda square by E plus twice f lambda plus g lambda square. And if we take a derivative, dk by d lambda, set it to 0, this will give us two directions, one which gives k max, the other which gives k min. Okay. Those are the principal directions or principal lines of curvature. Principal lines of curvature. Okay. We are out of time here, so I will stop the lecture here and continue. Thank you.